most of what we concentrated with so far with finding the orthogonal complement of a subspace is given a set of vectors and then putting it in a matrix and figuring out what the orthogonal complement is, but we really haven't done anything graphically. So I thought I would show you a graphical example of what we're thinking of when we do orthogonal complements. So let's say we take W as the intersection of the planes x plus y plus z equals 0 and x minus y plus z equals 0. And this problem asks you to find the orthogonal complement. So this is number 15, part C on page 316 of your text. My apologies, I meant to start this the presentation a little earlier. All right, so the first thing we're going to do is find a basis for the intersection of the planes. Think about how two planes should be intersecting each other. We should be seeing a line. So let's see if we really do get that. So a point, or a vector, if you will, that's in that intersection has to satisfy each equation. So we just solve the system, x plus y plus z equals 0 and x minus y plus z equals 0 like we usually would, and row reduce. And then we can easily see that the y coordinate, or the x2 coordinate, has to be 0, and the x coordinate has to be the negative of the z coordinate. So this is a free variable. If we let that be t, the x has to be minus t. So that's how we get these solutions. Again, I've written it as x1, x2, x3 here, but you could do x, y, z. Those letters really don't matter. But we really do see, we really do have a line here. All right. So let's see if we want to find the set of vectors that are perpendicular to this line. This is actually relatively straightforward if we think about how we've done orthogonal complement. So we have one vector that we want to find the orthogonal complement of. So we want to find the set of everything that's perpendicular to that one vector. Well, talking about what we've done with orthogonal complement in class, we know the orthogonal complement is the null space where we form a row space by looking at the matrix formed by the rows of the vectors that we're given. In this case, we're only given one vector. So putting that in a matrix and row reducing it is pretty easy, right? Because we just need to take that -1 and multiply through by it. All right. We also notice that this row space, one row vector, is perpendicular to everything in the null space. So if we have an x, y, z that's something in the null space, then I know that the 1 times the x plus the 0 times the y plus the -1 times the z has to be 0, or x minus z has to be 0. In space, in R3, this represents a plane, and this plane is the orthogonal complement. And that kind of makes sense, right? Remember that the orthogonal complement takes up everything else in the space. This is one-dimensional. The line's one-dimensional. We have 3 dimensions in R3, so we would expect a 2-dimensional object to be the orthogonal complement. So let's look at this graphically. So here are the two planes, this pinkish and bluish planes here, and this black line here is the intersection of those two planes. So now if I'm going to rotate a little bit so you can actually see the picture, but I'm going to take out these planes and put in the orthogonal complement. You really do see that here's the line and here is the orthogonal complement. I really do see something that looks perpendicular. This plane is perpendicular to everything in this line and vice versa. So I just wanted to go through this quick example to show you a little bit about orthogonal complement and graphically what it actually looks like.